Okay, so today we're going to start section 6.3. So we're going to continue with the idea of volumes and talk about volumes by cylindrical shells. So last time we talked about, when we did all those examples last time, the main shapes we used for the volumes that we were finding is we were using cylinders, washers. I think there's a triangular prism in there somewhere. And some other shapes, some other basic geometric shapes. And so I just want to recap, how we did all that and what we were talking about, just to kind of tie this all in together. So I started with the example of a cylinder, and we talked about how to find the volume of this thing. So any kind of volume. Especially for constant cross sections. I'll recap what that is in a second. So for constant cross sections, and all a cross section is you imagine, slicing into this shape, and you can do it in either direction, but the easier direction is, a shape we already know, circle here. So I imagine slicing into this, and what I get is, just a circle here. And so for constant cross sections, what I can do is I can find volume by taking. So I can find my volume by taking the area of the cross section times the length that the cross section goes through. So I imagine, dragging this cross section up and down the cylinder, and it fills out the cylinder. And let's say this cylinder has height h, just so we get the formula we're expecting. So for the cylinder, the area here is pi r squared for the circle. And then the length I go through is h, and we get the volume formula for the cylinder that we expect, pi r squared h. So what we were more interested in was non-constant cross sections. For non-constant cross sections, so for non-constant cross sections, so let's look at one of the examples we had. So I had something that looked like this. So I'm doing it like this just so I can integrate along the x-axis here. And the way we found this is, so if you look at the cross sections of this thing, if you look at a cross section here and a cross section here, the reason I call them non-constant is because the size of the cross section is changing as you go down the x-axis. So what we need to do for this one is we need to, look at one of these cross sections, and we need to find the volume of just a small one. So just like we've had approximating rectangles for integrals, we have approximating, solids for these volumes. And so if I want to find, the volume of this small cross section here, this small cylinder right here, let's say that length there is dx. So, I'm on the x-axis, I just go some small amount, we'll call it dx. And then the area of this thing is, just call it A. So then I can find the volume of that thing, which we'll call dV, it's a small volume. That's going to be the area of the cross section times the small length that I go through. And if I, do this, if I do the limit of this, and, I think about this in terms of limits and calculus, I'm going to make these dx's really small. I'm going to add up all those volumes. And so what is that? Well, it's an integral. So if I integrate these, the volume is going to be the integral a dx in this case. You might have y as your integration variable if you're going up the y-axis. I chose the x-axis here. But so the point is, there might be some shapes that we can't use, the volumes, the shapes we've already talked about here, cylinders, washers, which I've misspelled. And so we're going to talk about a new one. And we're going to talk about volumes by cylindrical shells. So here I have, something that would be a little difficult to use cylinders for, washers. It gets a little weird. So what we want to do for this one is, so I've already drawn it, but let's imagine and this is going to be, where I show off I can't draw again. Let's try and break this up into something that we can find the volumes of. So if I look at, if I take this line right here and I rotate it around this axis, and I've only drawn half the volume here because I can't draw in 3 dimensions, so I'm just going to draw, half of it. So if I imagine, rotating this around, I'm going to get, half of this, sheet, the sheet here. So it's like it's half of a cylinder in this case. And so what I can do is I can extend this thing, and I get a shape that looks like this. So it's a cylinder. It's kind of like the washer, where I have that, except now it's a cylindrical thing. So now I get these cylindrical shells. Is what they're called. And we want to be able to find the volume of the cylindrical shell. So again, we know that, so let's just call it, I'm not going to call it dB here because we're not going to do any limits. So I know that, again, volume is going to be, some sort of area times some sort of, distance here. So let's look for something that we know the area of. So if I look at, the shapes I have here, one thing I know the area of is the cylinder. So cylinders, and you can find area just like you do volume. So let's do the area of the cylinder first. So this is a surface area. So the surface area of the cylinder, I imagine, I can still, again, for a cylinder, do the trick that we were doing for the volume. I can break it up into a cross section, and the cross section of this hollow cylinder right now is, a length. It's the circumference, so that the cross section is a circle. And so what I can do is I can take, the length of this thing, so 2 pi r, and then multiply it by the height to get the area. So just like we could take, an area times a length and get a volume, here I can take a length times a length and get an area. So length squared is, of course, area. The area of the cylinder is 2 pi r h. Now to get the volume of the cylindrical shell, I'm going to take the cylinder, I'm going to multiply it by the length that I go through and get a volume. So let's call this length down here dr. So to get the volume, then my formula for that is going to be 2 pi r h dr. And so if I want to figure out so if I want to do, these new shapes that I've drawn up here, I'm going to need to determine what these things are, or what these quantities are. So what is r, what is the height, and then dr, whatever r is, that's going to be my integration variable now. So if I look at, something up here, if I look at the shape up here, let's try and fill. So I'm going to go ahead and turn this into dV. So looking at the shape up here, what I need to figure out for r is I need to figure out, this distance here. And the way, if I look at, what that r is, then that distance here is just the x value along the x-axis. So right now I have dV is 2 pi x, and now I need to figure out what the height of this cylindrical shell is. And the good news is that one's not too bad. If this function here is f of x, so this, so the first function I've drawn, so the original function that's in the book looks like that. We'll call this function f of x. Then the height is just given by the value of the function. It's the y value of the function, which is f of x. And let me not do that in red. So I have dV is 2 pi x, f of x, and instead of dr, I'm just going to replace it with what I've replaced r with. It's going to be dx. So my volume in terms of these cylindrical shells then is going to be the integral 2 pi x f of x dx. And so, you know, the advantage of this over the other ones I was doing is, you know, sometimes I'm going to have shapes that I can't do with, you know, cylinders or washers, but I also, you know, I've just written down a formula that's really easy to plug into. We might have to modify it if we aren't rotating around the y-axis, or if we are, you know, displaced from the x-axis, and we'll see examples of this. So I'm trying to keep the videos down under 10 minutes or around 10 minutes. So I'm going to stop here. So that'll be it.